Hello. Hi, good afternoon. My name is Abhishek Kumar Mehta, and today I would be discussing the consequences of taking the foundational aspects of mathematics, and when you extend it fully into quantum mechanical problems, what kind of consequences you can expect. So the main motivation of my presentation or my work is a very famous paradox within quantum mechanics itself. It goes by the name of Wigner's friend. And the paradox is formulated as follows. So if you have a quantum mechanical system which is being observed by an observer, which for the purposes of this paradox is called the Wigner's friend, and if assuming that this quantum mechanical system is just an electron, with an up state and a down state, the description of this system will be a pure state description. Essentially it's a superposition. But if in the paradox, if Wigner, who is standing outside his friend's lab, he decides that he is going to observe the whole system as a combined system, and he assigns a state u whenever his friend observes the electron to be in up state, and a state d when his friend observes the electron to be in down state. So from Wigner's perspective, the entire description is an entangled state description. So this is essentially a paradox, because depending on the observer and how the observer decides to package the entire system, he can write two different descriptions, and different observers can write two different descriptions. So the standard resolution presented in quantum mechanics is to impose something called the Heisenberg cut. So what that essentially means is that I am going to make a demarcation between all classical observers and all quantum mechanical systems. So whether it's Wigner or his friend or his friend's friend, they will always have a pure state description for the system. But the issue is, according to my opinion, obviously, is that this does not follow from the standard mathematics of quantum mechanics, and it's a imposition we do by hand. So if and now my aim is to figure out if there is a more natural way of imposing the Heisenberg cut, or is there a more natural analog of the Heisenberg cut? So to come to that, to arrive at that, I make to motivate this. If you observe that the Wigner's friend prescription is actually a state in some Hilbert space, but the Wigner's prescription of the same system is in a tensor product space. So essentially, what is happening is when you add more observers, the Hilbert space, you can naively say is undergoing some kind of a duplication. And this is actually a symptom of what we in mathematicians call paradoxical sets. I do not have a lot of time to go into the mathematical details, but by explaining what the Banach-Tarski paradox in mathematics is, I hope you will get a general picture. So the Banach-Tarski paradox in mathematics, it states that if you have a sphere and you can create a disjoint sets of that sphere, and you can do individual SO3 transformations on the sphere. So if you have your sphere here, you can create these two disjoint subsets, and individual group actions, SO3 group actions on these disjoint subsets can reproduce the original sphere. And the caveat here is that the disjoint subsets you are making, they are non-measurable subsets. So non-measurable subsets are not expected to be preserved under SO3 group of transformations. So their volume and area will not be preserved, and that is the reason why when you take a normal sphere and you are able to, when you take the disjoint sets, a group action can reproduce the sphere. So this allows you to, the Banach-Tarski paradox allows you to duplicate spheres this way. And the kind of group action that allows you to do that, they are called non-amenable groups. And what I have essentially shown is that the Hilbert space, the unitary group of the Hilbert space has a subgroup that is non-amenable, and it will have a similar kind of action on the Hilbert space, and it will allow you to create duplications of the Hilbert space. So hence the Banach-Tarski paradox in the quantum mechanical setting. So let me jump into the physical consequences of this. So because of Banach-Tarski duplications, you can take a Hilbert space and you can create multiple duplications using the group action. The group action being this specifically. What that means is that if you have a pure state in the original Hilbert space, in the duplicated space, it will obviously be entangled. And what that means, it means that the quantum mechanical particle will entangle with its own duplicates in simpler terms. And in the language of density matrices, it means that a pure density matrix will simply become a mixed density matrix. So if you take the mixed density matrix here, and if you partially trace out all the duplicates, this is what the general form looks like. And if you notice that if this interference matrix, in some papers it's also called the interaction matrix, I think, in Zurich's paper, I think. And if this is degenerate, you actually get back the pure state description. So there is no duplication. But in general, this is actually a random matrix, and depending on the ensemble, you can have two situations, two scenarios. So if you consider an ensemble with zero mean, if you work with an averaging over all these kind of partial traces, then you actually get the decoherence condition. And what this essentially means in simple terms is that due to Banach-Tarski duplications, a quantum mechanical particle will create its own environment. It will entangle with it and it will self-decohere. That is what this situation means. And the second situation where you are working with an ensemble that has a non-zero mean, these kind of ensembles, at least when I did a literature survey, was only was utilized for condensed matter systems like spin glasses. And what that essentially means is that you can find a way to map your partial traced density, density matrix to, you can relate it to the Hamiltonian of spin glasses. So that is what essentially means. So what is essentially happening here is that the paradox of being able to duplicate spheres is actually it's coming into quantum mechanics, and you can actually use Banach-Tarski duplications to create spin glass from simple quantum systems. Okay, I think I will end here. So,
if any questions.
Does it, I mean, the construction, does it only work for a harmonic oscillator, or is it infinite?
I have only tried it for harmonic oscillator, but it might work for other systems as well.
So does it require infinite dimensional Hilbert spaces? Because you're seeming to, I mean, the Banach-Tarski paradox requires this non-measurable sets. And so I'm wondering where, if I have just a qubit with two energy levels, levels, then
yeah, you are right. It is possible that when you are maybe for fermionic systems where you only have two energy levels, it might not work. So I have not tested it. Okay. So yeah, I have only tested it for simple harmonic oscillator. Yeah, you are right. It might not work for that. Yeah.
Okay, if no more question, let's thank the speaker.
Can I get 1 minute? I have to just make a final remark. I forgot to mention what is the resolution here. The resolution here is that one of the key components in the proof of the Banach-Tarski paradox is axiom of choice. So you just simply have to replace the Heisenberg cut with the axiom of choice. And that allows you to make all these kind of descriptions. So this is the resolution. Okay, thank you. Thank you so much.